Thank you for coming. Good afternoon, everyone. Let's get started. Inside a database, a code level walkthrough of an RDBMS I built in Python. My name is Keiko Kamijo. I'm a software engineer from the foot of the Japanese Alps. It's very cold. This talk is for beginners. Let me start by explaining what a database is. The Python RDBMS I'll show you today is called kpydb. I built it myself. kpydb is based on database design and implementation, a book that explains RDBMS internals using Java. I re-implemented its concepts in Python, using only the standard library. My goal in this talk is simple, to help you understand how an RDBMS works inside, without reading hundreds of thousands of lines of production database source code, and without being a C expert. Why did I build a database in Python? You can build anything with Python, even a database. So I thought I could learn Python and database internals at the same time. Here are the features of kpydb. It supports basic SQL enough to create tables, insert data, and query with conditions. It also has transactions and two types of indexes data types. Indexes, data types are integers and strings. It's a minimal RDBMS, but it has all the essential components. Using this, I talk about behind a single line of SQL, many mechanisms are working together. I'll show you what's happening inside when you run create table, insert, select, and delete. The algorithms I use are quite simple, not exactly the same as production databases like PostgreSQL, but I hope you understand the fundamentals and basic architecture of RDBMS. This talk won't cover usage of specific database products, how to write SQL, index strategies, performance tuning, or table design and normalization. This is the architecture of an RDBMS. When a database receives an SQL statement from a client, the parser analyzes it first. The parser has two parts, lexer and parser. The lexer splits SQL into tokens. The parser understands the meaning from those tokens. Then, the planner creates an execution plan. The executor runs that plan, interacting with the storage layer. In the storage layer, the buffer manager handles memory, and the file manager reads and writes to disk. Take select statement as an example. This is the select statement, select ID, name from users, where name is Alice. This returns a record where the ID is 258 and the name is Alice. Why is the ID a number like 258, not 1 or 2? I will explain later. For now, don't worry about it. First, the lexer. The lexer breaks the SQL into tokens, the smallest meaningful unit. It's like breaking a sentence into words before understanding it. Select, ID, comma, name, from, each becomes a separate token. The lexer also classifies each token by type. Keywords like select and from, identifiers like table and column names, delimiters, operators, and string returns. It's like how we classify words in natural language: nouns, verbs, adjectives. Here's the code that executes a select statement. Actually, there's a client that sends SQL to the server. But to keep things simple, I'm writing SQL directly on the server side now. How SQL is split into individual tokens. The tokenize method uses regular expressions to split the SQL into tokens. Find_all method extracts all matching tokens from the SQL string. Next, how the lexer handle keywords like select, from, and where. Keywords are defined here as reserved words. The lexer class has a match keyword method that checks if the current token matches a reserved word. There is also a need keyword method. This method checks the reserved word and advances to the next token. Because each keyword method contains next token method, it processes token from left to right only once and moves on to the next parsing step. The lexer recognizes identifiers and starts processing. There is a match ID method that checks if the current token is an identifier, and an id ID method that recognizes an identifier and advances to the next token. There are similar methods for delimiters, operators, and details. Next is syntax analysis. To a computer, SQL is just a sequence of tokens. The parser structures them into something meaningful. The result is called an AST, abstract syntax tree. An AST is a tree that represents your SQL query in a structured way. As you can see, it has a tree structure. Select columns from table, where condition. The SQL we used today is too simple to show the tree structure clearly. But with a complex condition like this, the tree structure becomes easier to understand. For example, say I'm shopping for souvenirs. I want dried mango or banana chips under 200 pesos. Here's where the parsing starts. The parser processes the column list. This is the query method, the entry point for parsing a select statement. First, each keyword recognizes the select token and advances to the next one. Then, select list processes the column names. The select list method parses column names. First, it appends the first field name to the list. Then, it appends the first field name to the list. As long as commas continue, it appends the next field name. Finally, it returns all field name as a list. The parser processes a table list. We are back to the query method. Next, it recognizes the lam keyword, advances to the next token, and builds the table list. This is a table list method. You've already seen this pattern with select list. Table list does the same thing. Loop through commas and collect each table name and return them as a list. Next, it recognizes the where keyword and builds the condition expression. A predicate is a condition like name is Alice. The parser processes the conditions. The predicate method builds the condition expression. A predicate can have multiple terms connected with AND. It starts by calling the term method to parse a single condition. The term method builds a single condition like name is Alice. It starts from the left side. The expression method figures out whether it's an identifier or leaders. Once it hits the equal sign, it does the same for the right side and return the complex condition. When conditions are connected with AND, it recursively calls the predicate method to connect them. Now we are back to the query method. We have the fields, tables, and conditions. We put them together into a query data object and return it. This is the ASD. This is a screenshot from the debugger. You can see that query data is structured. The planner receives the ASD and creates an execution plan. It decides which table to access and in what order to return records. For example, when joining multiple tables, production RDBMS use statistics and indexes to choose the optimal plan, but here we create a simple execution plan. The parser has created the ASD after validating the values and the expressions. We pass it to the query planner to create the execution plan. We create the execution plan. First, we create a table plan to decide which table to access. Next, we add a select plan to filter records using the where condition. Finally, we add a project plan to extract only the specified fields. Note that select in select plan does not mean the select statement. It means filtering with the where clause. These names come from relational algebra. Looking at the debugger, you can see project plan contains select plan, which contains table plan. This is pipelined query processing. We don't need to create intermediate tables, which makes processing more efficient. The executor receives the plan and creates scans. The execution object. Table scan reads rows from the table, select scan filters by condition, and project scan extracts fields. To understand how the execution engine works, we need to understand the storage layer first. So we'll move on to the storage layer. The storage layer consists of buffer manager and file manager. The problem we want to solve is we want to handle large data, but also processes it fast. These are conflicting requirements. Disk access is much slower than memory access, so the RDBMS manages memory itself, not relying on the OS, and ensures data persistence. Let me explain some terms. A block is a fixed-length data unit for storage. In kpydb, one block is 400 bytes. A slot is a fixed-length area within a block for storing records. Table information determines the slot size and layout. One block contains multiple slots, and one record is stored in one slot. The buffer manager enables the RDBMS to manage its own memory instead of relying on the OS. It keeps frequently accessed blocks in memory for fast access and removes less used blocks to make room for new data. The file manager handles data persistence. It uses the OS file system and reads and writes in block units. Back to the executor and see how it actually retrieves records. We have the table plan for users, so it reads blocks of the user's table from the storage layer one by one, and searches for records slot by slot. Earlier I said that table information determines the slot size and layout. Specifically, it's based on create table, ID is int, so 4 bytes. Name is Butcher, 10, so 10 bytes. For strings, we also need 4 bytes for the size information. At the beginning, there is a status flag. 01 means in use, 00 means empty. So we know the slot size and the layout inside. One slot is 22 bytes, so we search 22 bytes at a time. For each slot, we check 10 bytes starting from byte 13 to see if name is Alice. If it matches, we return the record and output the specified fields, ID 258, name Alice. Now that we understand the storage layer, let's go back to the select statement and see how data is actually retrieved. Here is the code. At this point, the plan is ready. We call the open method to start a scan. Let's look at how table plan works. reading records from the user's table. Based on the table definition, it checks the field type. Then it calls getInt method or getString method to return the value. This is an example of the getString method. It specifies a field name in the current slot and returns the value. Next, filtering records by the condition. The next method of the selectScan class checks in a loop whether the condition name is Alice is satisfied. Finally, project plan extracts only the specified fields. The getValue method of project_scan extracts only the specified fields. We call scan close method to finish the executor. Then commit and we are done. When we run it, ID 258, name Alice is output. Next, insert and delete statements. We add a record with ID 259 and name Bob. First, we find a slot with status flag 00 empty. Then, we use write-ahead logging write logs first for failure recovery. Finally, through the transaction, we write the data to the empty slot. Creating and executing the plan is the same as select. getFields method gets the list of field names, and setValue method sets the value to each field. Close method closes the scan and returns the number of processed records. The write method to file manager writes data to the specified block in the file. When deleting a record, the data is not deleted immediately. Using the transaction, we just update the slot status flag to 00. The actual data remains in the slot. Later, when adding new records, this slot will be used as an empty slot. The delete method updates the status flag of the specified slot to empty. Looking at the debugger, at the yellow star, Bob's record was added after Alice. When we select from users, two records are output, Alice and Bob. After we delete Bob, only Alice is output. Here's the actual binary file. On the left, hexadecimal values. On the right, ASCII characters. Yellow, first 4 bytes, status flag. Light blue, next 4 bytes, ID. Light pink, next 4 bytes, string length. Dark pink, next 10 bytes, name. You can see the data is saved according to the slot layout. Now, Pay attention to how the int data is arranged. Doesn't it look different from what you'd expect? Here's the conversion. 258 in decimal is 0102 in hexadecimal. 259 in decimal is 0103 in hexadecimal. But in the binary file, the bytes are stored in reverse order. Endianness refers to the byte order used to store data in memory. Little endian stores the least significant byte at the lower address. So 258, which is 0102, is stored as 0201. Big endian stores the most significant byte at the lower address. So 258 is stored as 0102. Why is this important? When exchanging binary data between different systems or network communication, which uses big endian, you need to pay attention to this. Neither is better than the other. Both exist for historical reasons. By the way, the CPU in my Mac is used little endian. In Python, you can use the struct module to convert values to byte sequences with a specified endianness. Less than means little endian, greater than means big endian. Exclamation mark means network byte order, which is the same as big endian. The I stands for int type. Summary is, the Rexer breaks SQL into tokens. The parser builds an ASD from tokens. The planner determines the optimal execution order. The executor accesses data according to the plan. The Python manager keeps data in memory. And the file manager handles endian conversion and reads and writes to disk. I hope you understand that many mechanisms are working behind a single line of SQL. Unfortunately, we are out of time, but there is so much more to explore. Indexes, logs, transactions. I wish I could have covered these topics, but the source code is all there. Please check it out on GitHub. If you clone the repository, you can learn SQL from the client. As for my next challenge, I want to build my own browser and embed kpydb as its storage engine like LevelDB in Clown. I haven't implemented it yet, but the name and icon are ready. Kelon. Keiko, my name, plus Kero, the sound a frog makes in Japan. That's all for today. Thank you for listening.